Writing the constraints and objective functions for linear programming is very important. Constraints are limitations placed on variables. In linear programming, constraints are written as linear inequalities, while an objective function, or functions, are used to find the greatest or least value for some particular constraint. Let's take a look at an example that has to do with furniture manufacturing. A furniture manufacturer makes two types of furniture, chairs and sofas. Manufacturing of a chair requires 6 hours of carpentry, 1 hour of finishing, and 2 hours of upholstery, while manufacturing a sofa requires 3 hours of carpentry, 1 hour of finishing, and 6 hours of upholstery. Due to limited availability of skilled labor as well as of tools and equipment, the factory has available each day 96 labor hours for carpentry, 18 labor hours for finishing, and 72 labor hours for upholstery. What that means, if we take a look back at the 72 labor hours, it means that there are 72 hours of labor that they can dedicate every day for upholstery. Now, after all that work, there are of course costs, and so after things have been paid, the profit per chair is only $80 and the profit per sofa is $70. The question is how many chairs and how many sofas should be produced each day to maximize the profit. Well, down below I have a table that's been already established. A lot of times writing and setting up the tables is the most difficult piece. But once the table's set up, then it's a matter of putting the information in. And the way I decided to set up this table has to do with the fact that we have chairs and sofas. And with chairs and sofas, there are 3 different things required to actually make them. Chairs and sofas have a profit, and there are hours that are constraining how much carpentry, finishing, and upholstery we can do. So let's go back through the problem and take each piece of information, plug it into the table. Manufacturing of a chair requires 6 hours of carpentry. So chair, 6. 1 hour of finishing, 2 hours of upholstery. Now, the sofa requires 3 hours of carpentry, 1 hour of finishing, and 6 hours of upholstery. We know that due to limited availability of skilled labor, as well as of tools and equipment, the factory has available each day 96 labor hours for carpentry. No more, but it could be less. So for carpentry, it's at most 96. So I write less than or equal to 96 there. I could also write the words at most 96. We can't go over 96 labor hours though, so it can't be greater than that. Labor hours for finishing is 18 at most, less than or equal to 18. And for upholstery, 72, less than or equal to 72. The profit per chair is 80, and the profit per sofa is 70. With this information, we can write the constraints. Constraints are written as a system of inequalities. They're the carpentry, finishing, and upholstery. I'm going to let the letter X represent the hours devoted for, X is going to represent the number of chairs, and Y is going to represent the number of sofas. So my first inequality is 6x plus 3y is less than or equal to 96. My second inequality is 1x, or just x, plus 1y, or just y, is less than or equal to 18. And for upholstery, we have 2x plus 6y is less than or equal to 72. There are my constraints. So the objective function is what I want to maximize or minimize. And in this case, it tells me I want to maximize the profit. So I want to figure out what will give me the greatest profit under these constraints. And profit is calculated as $80 times X, the number of chairs, plus 70 times y, the number of sofas. Once the constraints are written and the objective function is written, there's one other piece to remember, and that is that x can't be a negative value. So we know it's greater than or equal to 0. And y also cannot be a negative value. We can't make negative chairs or negative sofas. Once we have the constraints, objective function, and reality placed in, I usually graph these. And graphing works best with technology. We used to have to do these by hand, but now that technology is such an easy resource, we have lots of options. Technology makes graphing the constraints much easier. 6x plus 3y is less than or equal to 96 is our first constraint. The second constraint is x plus y is less than or equal to 18. Our third constraint is 2x plus 6y is less than or equal to 72. Now that's supposed to be a 2x. Our fourth constraint is x is supposed to be greater than or equal to 0, and y is greater than or equal to 0. Now our graph is pretty difficult to see because all these colors are laying on top of each other. What I like to do at this point is reverse how the shading is going. Right now, all the shading in Desmos is showing where all the true solutions are, and it's hard to figure out where all 5 colors overlap. So what I like to do is I like to go back up to where my inequality is, and I like to change that from a less than or equal to a greater than or equal to. And similarly, I like to take this next one, which is also less than or equal to, and change it. What I'm doing is I am, instead of shading the true solutions, I am shading the false solutions. And now the white region is what's called our feasible set. So this white region over on the website is providing the answer or answers that make all these constraints true. In a different video, you'll learn about identifying the parts of this feasible set that actually maximize this profit that we are looking for. This video will leave it here.